This is the last question from the 2025 AP Calc AB for your response set. It's a no calculator question here that gives us a curve G defined by this implicit equation. In part A, we're asked to show that the derivative of y with respect to x for this equation is equal to the fraction that they provide us with. So when you use implicit differentiation, you need to assume that y is a function of x. So when I take the derivative of y cubed with respect to x, I'm in need of using a chain rule. Here's the derivative of the outside function with the inner function left inside. I'm finishing my chain rule by multiplying by the derivative of the inner function. I'm using a similar approach for the derivative of y squared. So I'm subtracting off the derivative of y squared. Multiply by the exponent, subtract 1 from it, inner function copies into that, times the derivative of the inner function, subtract off the derivative of y with respect to x, and then add on the derivative of 1/4 x to the 1/2 with a power rule. No derivative necessary on the other side. Derivative of 0 stays at 0. I want to isolate dy dx. So the first thing I realized is I can subtract 1/2 x from both sides. Now as I did that, I saw that there was a minus x up here and a 2 down here. So I thought it's probably going to be to my benefit to write that as minus x over 2 rather than having the fractional coefficient of x showing up on that side. Should make an easier transition to what I need to try to show here. I then have dy dx remaining in every single term that remains on the left side of the equal sign. If I factor dy dx out as a common factor, I'd be left with 3y squared minus 2y, and then minus 1 when I remove dy dx from itself. And if I divide the negative x by this set of parentheses, so have this set of parentheses join the 2 in the bottom, I have confirmed what I was trying to show in part A. Part B says there's a point on the curve G near the location 2, -1 that has an x-coordinate of 1.6. We want to use the line tangent to the curve at 2, -1 to approximate the y-coordinate of point P. So I'm going to build my tangent line equation at this ordered pair, and then I'm going to use that tangent line equation to make an estimate for the y-coordinate at 1.6. So I'm going to find the slope of my tangent line evaluated at 2, -1 by putting 2 in place of the x in my derivative and -1 in place of the y's in that derivative. This does not have to be simplified. If you do try to clean it up a little bit, what you should end up with is you should end up with -1/4. So the slope of my tangent line is -1/4, and the point of tangency is 2, -1. So I just built a point slope form for the equation of that tangent line right here. Now if I want to estimate the y value that corresponds to the x value of 1.6, I'm going to use the y value from this tangent line in order to establish that estimate. So if I wanted to solve this for y, I'd subtract the 1, so you see the -1 showing up here. And I'm also plugging in the x value of 1.6 to determine the y value on this tangent line at 1.6 and use it as my estimate for the y value on the curve at that spot. This right here would receive full credit. If you simplify it, should simplify to -9/10. For x and y being positive, there's a point S on the curve G where the line tangent to the curve at that point is vertical. We're asked to find the y-coordinate of point S and show the work that leads to your answer. So think about a vertical line. A vertical line has an undefined slope. If it's a tangent line that's got an undefined slope, that would mean our derivative has to be undefined, meaning the denominator of our derivative would have to be 0. So if I set the denominator of the derivative equal to 0, I can solve this by factoring. So if I factor what's inside the set of parentheses, I should end up with 3y plus 1 and y minus 1. This is never equal to 0. This factor is equal to 0 when y is equal to -1/3. That doesn't satisfy part C because we're supposed to consider positive values of y. But this, y minus 1, is equal to 0 when y is equal to +1. Find the y-coordinate of point S. Don't even need to plug in to the original equation to find the corresponding x. We have found the y-coordinate of the location on the curve where x and y are both positive, where the tangent line is going to be vertical. Part D says that a particle is moving along a curve h. Curve h is defined by this implicitly defined equation. At the instant when the particle is at the point 4, 1, dx dt, so the rate of change of the x-coordinate with respect to time is positive 3. We want to find dy dt at that instant, and we want to show the work that leads to our answer. So what I'm going to need to do with this equation that defines h, where a particle is moving along it, I'm going to need to find the derivative of both sides of this equation with respect to t so that I can generate a dx dt, making me capable of utilizing this and then allowing for me to find what the value of dy dt is at that spot. So both x and y are changing over time. So when I take the derivative of 2xy, I'm in need of using a product rule. The derivative of 2x with respect to t is going to be 2 dx dt times the original second part plus the original first part of the product. And then the derivative of the second part of the product is going to be dy dt. I'm going to add on the derivative of natural log of y with respect to t. So that's going to require a chain rule. So I'm going to have 1 over the inner function and then times the derivative of the inner function. And then don't forget to take the derivative of the other side of the equation. Now what I want to do here is I want to figure out at the ordered pair 4 for x, 1 for y, what the value of dy dt is. So I went ahead and I put 4 in place of my x, I put 1 in place of my y's, and I put positive 3 in place of dx dt. Now you will notice a change in my notation here. I did need to denote that once I start plugging in, this is the value of dy dt evaluated at 4, 1 that appears in this spot and that appears in this spot. Now if I multiply these together, that gives me a 6, and if I move that 6 to the other side of the equation, it becomes a negative 6. I've got 8 dy dt's at 4, 1 here, plus 1 more dy dt at 4, 1 there. That's 9 total. Dividing both sides by 9 gives me my value of dy dt evaluated at 4, 1 to be negative 2/3.